This is project 6 video number 1, the pencil and paper part. You're supposed to write a function that for a uniform sphere of charge takes two arguments, total charge, I'll call it capital Q, and the radius R, and produces a graph of the electric field as a function of the distance R, little r, from the center of the sphere for R is equal to 0 to R is equal to 3R. Alright, let's use Gauss's law to get an expression for the electric field in two different regimes. So here's our ball of charge, total amount Q, uniformly distributed throughout it. And suppose I want to find the electric field at some point in space, a distance R. Well, no matter where I am, if I'm R away from the center of the charge, I'm going to have the same electric field. From symmetry, the electric field's got to be outward and the same value at all points, the same distance away. So that's all my symmetry arguments, little r right there. And I'll say from Gauss's law, this will be my Gaussian surface, an imaginary surface. And we have integral. So the electric flux outward through a closed surface, and that's phi sub e, where the integral of E dot dA over that entire surface is equal to the charge enclosed divided by the constant epsilon 0. Now, because the electric field is outward everywhere and dA is outward everywhere, this becomes E times dA, where, and I'll say is equal to Q, doesn't look much like an equal sign, equals Q in over epsilon 0, because E is parallel to dA. And then I can factor out the E, but only because it's got the same magnitude at all points on the Gaussian surface. So this is because E same at so this is just the magnitude at all points. The distance at, let's say, same distance from center. So I'm integrating on this surface, and all points on that surface are a distance r away from the center, and and E is the same at all those points, so I can factor it out. So then this just becomes E times the sum of all the dA's, just the area of the circle, which is for the area of the sphere. This is a spherical surface here. I get a little 3D effect there. 4 pi r squared, and this is the charge inside is the charge density times the volume inside, the volume of this little sphere of radius little r. Now the volume, let's figure out what the charge density is first. Because the charge is uniformly distributed, the charge is a constant, so I can take the charge density to be, this is V sub little r, this is Q divided by V sub big R. Times v sub little r over, I guess I'll try to write it the same way so it looks like pure substitution, over epsilon 0. Alright, now the big R is 4/3 pi times big R cubed, and that's the big volume, and the little volume is 4/3 pi times little r cubed, and then all of this is to be divided by epsilon 0. So we got, let's see what we had all the way over here, by the way. Yeah. This is equal to, let's see, the 4/3 cancels out. 4/3 divided by 4/3 is 1. Pi over pi is 1. And we got Q R cubed over epsilon 0 capital R cubed. And that's E times 4 pi little r squared. So divide both sides by the little r squared and 4 pi, and I get E is equal to 1 over 4 pi epsilon 0 times Q over R cubed times little r. This is equal to our familiar Coulomb constant K, so I choose to call it that. So it's K capital Q over R cubed times little r. So from 0 out to, as long as I'm inside the sphere of charge, that works. And I got a result that we have seen before. So I can put a little box around that. This is inside. So inside. Then if we choose a point where we're trying to calculate the electric field that's outside the ball of charge. So here's our ball of charge. There's the center of it, and I choose a Gaussian surface. That's a perfect sphere. With a radius, I'm going to call it lowercase r, that's bigger than the radius of the ball of charge, which is capital R. So sometimes little r is bigger than big R. I never put the capital R in this diagram. Alright. So first off, we know from early in the course that it should just be kq over little r squared, where q is the total amount of charge on the ball. That's that. I'm going to use capital Q for that. And but let's get it from Gauss's law. So the integral of E dot dA over my Gaussian surface, and I'm choosing this big one, is equal to Q in divided by epsilon 0. So from, like before, the electric field from symmetry is outward, or could conceivably be inward if capital Q is negative, but I'm just going to call it outward. Therefore it's going to be parallel to dA at every point on the surface, and all points on the surface are the same distance, little r, from the center. So from the symmetry of the charge distribution at all points on that Gaussian surface, the electric field has one and the same value. So the first bit means I can say EDA is equal to Q in over epsilon 0, because E is parallel to dA everywhere. That's my justification, and then I can factor the E out. Equal Q in over epsilon 0, because E has same value, Control C, value at all points, same distance from the center of the charge distribution. I'll just say from center. Alright, and then this is just E times A, because the sum of all the dAs is the total area, and that's equal to the amount of charge that I got inside this surface is all of it, capital Q, over epsilon 0. So this becomes E times 4 pi. Now this is the area of my Gaussian surface, so that's little r squared is equal to Q over epsilon 0. So E is equal to Q over 4 pi epsilon 0 times 1 over r squared. And the 1 over 4 pi epsilon 0 is just K. So we have just what we thought we were going to have. E is equal to K Q over r squared. So this is good for outside. So for r greater than or equal to 0 and less than or equal to capital R, E is equal to, I think I'm going to have to look at it, but something like K Q over R cubed times little r. Let's take a look. KQ over R cubed times little r. And for R greater than or equal to 0, I think I'll put it the other way. R greater than or equal to capital R, E is equal to K Q over R squared. At capital R, it's like I can't make up my mind. I'm saying both of these are good, but if you check it out, when little r is equal to capital R, if I plug it into this one, I get KQ over big R squared. If I plug the capital R into this one, I get KQ over big R squared. So either one of them is good there. So here's my game plan. I get values of Q and capital R as arguments. I'll initialize K, in other words, set it equal to 8.99 times 10 to the 9th Newton meter squared per coulomb squared are the units, but I'm going to just go with the value. And I think I'm going to create an array. I think I'll go. I want to try to be clever here. For the straight line portion, I really only need 2 points. For the curved portion, I'm going to use a bunch of points to smooth it out. So I'm going to work on the curved portion first. So I'm going to let little r equal an array, linspace 100 values. I'm going to try from capital R to 3 times capital R, and I think I'll try 101 values. And then E for that region, from R out to 3R, I'm going to have E is equal to, I'm hoping to see different ways of doing this, like indicate that you guys have figured out how to code it up, and you want to use your own ideas rather than mine. So you come up with your own plan, and you look at mine, you say, yeah, you say to yourself that your own plan is going to work, and so you stick with that. But because this one, I haven't done it this way before. I'm trying, take advantage of the fact that it's a straight line out to there. So then E is equal to K times Q, which is something that was given, divided by, and I'll go dot slash because R is an array, and I wanted to do it for each of these 101 values in that array of values. And the same thing with R dot to the power of 2. So it's more like I'm writing the code here rather than just an outline in English, but that's what I want to do, create an array of electric field values. Okay, now I've got the issue that I'm not ready to plot yet because I haven't gone from 0 out to capital R. But the thing is, at R, I've actually calculated it once, and I used the second expression. But remember, I just verified that at capital R, both expressions are the same. So I'm going to say 5. I'm going to try to add one more element to the array, namely 0. So I'm going to say R is equal to 0, comma R. If you're just filling up an array with numbers, like you only want to put 4 numbers in an array, you use these open brackets, assign it to a variable, and you might go 0, comma 1, comma 5, comma 8, for instance, close bracket, and you've just created an array of however many numbers I just said, I think 4. This says create an array that has the first element is 0, and then the next, however many elements are in R, elements, which are the elements that were already in R. This is kind of weird. I'm then assigning the result to the variable R, so it changes it. And also, I want to say E, which is an array of 101 values, calculated values of E for little r is equal to capital R out to 3R. I'm going to say same thing. At 0, E is 0. You can see from the first function I had up here, that's the case when little r is equal to 0. So at the center of the charge distribution, the electric field is this constant times 0, which is just 0. So I'm using that and say E is equal to that, comma, the 101 values that it was before. So now presumably R and E both have 101 values, and then plot. It's always plot x comma y. Keep in mind that's got to be a lowercase p when you type it in. So I'm plotting R along the x-axis and E along the y-axis. So that should look good. Then of course gotta fix it up, but I want to try that. That's my plan, and that represents the pencil and paper part for project 6.